In the previous video, we talked about streamline, we talked about pathline. Okay, we talked about streamline, and then we know the equations u and v, and then nonetheless we have some other equation that can describe u and v, which is u equals to partial xi over partial y, and v is equals to minus, this thing. So, and then we derive a general derivation to describe a simple stream function. Okay, you also know that this thing how you derive. So I will suggest you go and know and understand how to derive all these things. And then we derive using the same method from here. Okay, we derive a string function for a stray case. Okay, which is the totally same thing as this. I mean the xy. If you remember our stream constant is equals to our stream function is equals to xy in this case. So how does this relate to their stream function? I have no idea. Okay, um, but they should be the same. But nonetheless, yeah, there's some. Hold on. So you may ask me whether is this equation eventually will derive the same answer for what is being shown over here. I think maybe yes, because wherever a value and c values are being calculated throughout over here. Okay, it's all being set up. A is being utilized. A is equals to 0.3, and then you do all this stuff and yeah, integration and stuff. So I may be wrong, but nonetheless, this is the thing. And then we talk about visualizing the streamline flow, and we also talk about how different. We also derive an equation for x and y. Okay, we also explain that different equations for x and y will have this one is exponential one, but if let's say if it has a square root, then you have a different form of a graph itself, as you can see. So this is pretty interesting. Yeah. So and then now we talk about finding the. Also, nonetheless, last video we talk about finding the position of the particle. It's a simple math, and then you use a velocity magnitude to actually problem solve. I'm pretty tired. So in this video, we talk about how to actually find the velocity magnitude, a comment on whether whether is it decelerating or accelerating. Because it's pretty important because you want to know whether you don't know whether you have this graph over here, but you don't know whether the particle is moving in this direction or moving in this direction. But in this case, because we are talking about time, because e to the power of if you remember our equation is in terms of this one, right? E to the power of time t. So this is why yeah. But nonetheless, it's more safe because as the function becomes more complicated, you can't actually explain whether it is going here or it's going here or what, and whether it's the time itself. Yeah, nonetheless, yeah. So let's prove it for you. So where am I? So hold on a while. So the purpose is actually to know whether the velocity slow down or go faster. Okay, of the particle, the velocity of the particle. So to solve, we know u equals to ax and v equals to minus a1 again. And then we add t equals to 0. Okay, none as I say so simply, but just that saying that u and v in this case is only dependent on the equation of the velocity. If the equation of the velocity is different, okay, it is some weird stuff, you have a different approach. Okay, what you sub in for u is totally different. It will not be ax, it will not be minus ay, it will be something else. Nonetheless, let's come back to this thing. So at t equals to 0, okay, you know that u naught is equals to 0.3 times 0.2. Okay, where do I come from? I just come from this the previous equation we have derived. This general equation 0.2 EAT. Okay, so when you sub in 0, okay, everything becomes 0.2. And then we also know that a equals to 0.3. So this is why this is A, and this is the equation over here, E EAT. Hold on a while. Correct. So because this is x value, so when calculating x is equals to this equation. Okay, and then ax, because now we're talking about u equals to ax, so a itself comes in again. 0.3 times 0.2, you have this one, and for v is minus ay, so you use the same equation, and eventually you get this one. You do a simple Pythagoras system, you get the trajectory, the speed itself is 24 meter per second when it's at time equals to 0, and then last video we talked about at t equals to 6. Okay, and then the same applies. So this is ax. Okay, x, in this case we sub in t equals to 6, and then you have x value with us. So this x value is actually 1.21. You multiply by a, which is 0.3, you get this value, and same as this, Pythagoras theorem again, and then you get this one. So from here you can see that 24 meter per second and 3.9 is actually decelerating. And if you were to prove in a more theoretical way, you can actually use the gradient method. Okay, so we will take u0 minus u6, and then divided by v0 minus v6, because you know u is the velocity in the x direction, and while v is the velocity at the y direction. So you can just do a simple thing, and then you can see that it's a minus 0.015. A minus gradient means that it's actually decelerating, and you can state that it's actually negative gradient and we are decelerating. Okay, so answer the fifth question. Also show that the streamline and pathline have the same profile if the flow is considered to be steady. So if this flow is actually steady, let's come back to the video that I've actually used. You can see that as I explained earlier, the velocity, this is the path line, right? The red color is the path line. So at this point, it's somewhat parallel to the streamline itself, as you can see. So their profile somewhat is actually the same. Okay, they're actually the same. So
red lines are the path lines, and what you can see here is that at each instant,
so yeah, I hope you get what I mean. So at this point, you can see the streamline and pathline are traveling in the same pathway. Okay, the same profile. And then the profile itself, I also don't know what is actually they are talking about. So nonetheless, yeah, what I would understand is that the profile itself, they're actually parallel.
again
So
in
with
black,
this
but now I've
flow,
released 4 different particles, marked particles, and calculated 4 different path lines as a function of time. 1, 2, 3, and 4. And you can see they follow along these red trajectories. The red lines are the
so you can see it actually say that the streamline follows the path line. So the movement itself, it follows all of these things. So yeah, it explain. So when it's steady, okay, so what is if it's not steady? Okay, so what I mean. So as you can see, when the flow comes in up until about this point, okay, it's always steady, is laminar, okay, it's laminar. As I say, steady is laminar, while unsteady is turbulence in the very, very early part. So this portion is turbulence and is unsteady, and therefore the streamline and the path line itself all are pretty much um, more complex to actually analyze. I can't explain much because I have lesser experiences, but you can feel free to go back to this three thing to actually watch. And nonetheless, I said earlier, straight lines, we are not talking about it, but it is good to know. So in the next video, I'll just do a quick talk on this one. Okay, stream function is used to get the flow rate. Then we'll do a summary at the last second video, and we'll call it a day. So see you.